Hello. Welcome to the webinar today. My name is Jennifer Nyman. I am a Senior Engineer at Geosyntec Consultants in Oakland, California, and I assist with the coordination of the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's call. The webinar today will consist of a brief overview of SERDP and ESTCP by Dr. Andrea Leeson, followed by a list of upcoming webinars in the series. After Andrea's opening remarks, we will transition to the technical portion of the webinar. Today's event features two presentations on realistic expectations for geophysics when used for site characterization and remediation monitoring. Today's webinar is the second of a two-part series titled Geophysics 101. The first webinar was offered on June 30th. Slides and a recording of that webinar are posted on the SERDP and ESTCP website. On today's call, Dr. Frederick Day Lewis of the USGS Office of Groundwater Branch of Geophysics will present geophysical characterization and monitoring studies and discussing hydrogeologic framework and processes. Dr. Day Lewis's presentation will be followed by a brief question and answer session. Then, Ms. Carol Johnson from the USGS Office of Groundwater Branch of Geophysics as well will discuss borehole geophysical logging. Ms. Johnson's presentation will be followed by a second question and answer session. We will conclude the webinar with an interactive Q&A session with both speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. And in fact, we encourage you to submit your questions in advance of that session. On this slide, we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of SERDP and ESTCP, as well as the Program Manager for Environmental Restoration. Andrea has been with SERDP and ESTCP since 2001. Before that, Andrea was a research scientist at Battelle Memorial Institute, where she conducted research on in-situ bioremediation. Andrea?
Thanks, Jennifer, and welcome everyone to today's webinar. SERDP is the Strategic Environmental Research and Development Program and was established in 1991 by Congress as a partnership between DoD, the Department of Energy, and EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. We fund both fundamental research as well as advanced technology development under SERDP that ultimately impacts real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs, with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in SERDP, 5 in ESTCP. The energy and water program area is only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and climate change, and weapons system and platforms, are SERDP and ESTCP programs that are managed jointly by a specific program manager. Our webinar today is focusing on research and demonstrations that were conducted under the Environmental Restoration Program area. Environmental restoration has essentially 5 main areas of research. We have contaminated groundwater, contaminants on DoD testing and training ranges, contaminated sediments, wastewater treatment, and risk assessment. Our webinar series will be highlighting research and demonstration efforts from all 5 of our program areas. This slide here is showing our upcoming webinars, and as you can see, we'll be covering a broad range of topics, and registration is now live on our website for each of these webinars. The next webinar, based on research and demonstrations under the Environmental Restoration Program area, will be on September 8th and will focus on SERDP efforts on redox-based groundwater remediation technologies. You can find more information about our upcoming webinars on the SERDP and ESTCP website at this link, and I hope you enjoy the webinar today. Jennifer?
Thanks, Andrea. It's now my pleasure to introduce Dr. Frederick Day Lewis. He's a research hydrologist with the USGS Office of Groundwater branch of Geophysics. Fred's research focuses on the development and evaluation of geophysical technologies for aquifer characterization and monitoring natural and engineered hydrologic processes, including aquifer remediation, groundwater surface water interaction, and aquifer storage and recovery. Fred has served as the principal and co-principal investigator on multiple research grants developing and testing new geophysical methods to aid in site characterization and performance monitoring. He has authored more than 50 peer-reviewed papers and book chapters, and he is a fellow of the Geological Society of America. Dr. Day Lewis received a doctoral degree in hydrogeology from Stanford University. Fred?
Thank you very much, Jennifer. As Jennifer said, this is the second in a series of webinars we're giving on geophysics, titled Geophysics 101. And today I'll be focused on case studies, applications of geophysical methods to characterization and monitoring. I'll begin by outlining some of the challenges faced in groundwater studies at remediation sites, including understanding the hydrogeologic framework and tracking changes in aquifer properties, water quality, and contaminants. I'll present a few hydrogeophysical characterization studies and discuss geophysical opportunities to assist in hydrologic characterization. The case studies for characterization come from Hill Air Force Base in Utah, and this is a case study in the literature outlining, or highlighting rather, the use of seismic refraction for a framework, and then a second study at the Hanford, Washington site. Hydrogeophysical monitoring studies include case studies at Brandywine, Maryland, which is one of our ESTCP projects, and also at the Naval Air Warfare Center in West Trenton, New Jersey, another ESTCP project. I'll wrap up by including some messages to just help avoid being oversold on geophysics. Geophysics has incredible potential to assist in characterization and monitoring, but there are also limitations, and those limitations are very real, and we want in our project to communicate those as well through our tech transfer efforts. The key message of my talk today is that when used appropriately, geophysical imaging technologies can help resolve the hydrogeologic framework that controls fluid flow and solute transport. It may provide indirect information on contaminant plume distribution, but it's important to remember that that information is indirect. Also, we can sense changes related to injections, for example, for biostimulation, and changes that occur in aquifers as a consequence of remediation and biological activity. So the first challenge that I want to discuss is understanding the hydrogeologic framework. Using conventional borehole data, characterization is an expensive proposition, and we're always faced with having to fill in the gaps in between where we sample. When we look at cores from wells, or when we look at samples from wells, or when we conduct hydraulic tests at individual wells, you're looking at a very small sampling volume around that location. And then you have very large gaps in space in between those locations that we seek to fill in traditionally with interpolation methods, geostatistical methods, or geologic correlation. But this is problematic in the presence of subsurface heterogeneity, where we can have hydraulic properties varying by orders of magnitude over short distances, especially in heterogeneous aquifers and fractured rock. Also, drilling can create unwanted hydraulic pathways and disturbances around boreholes that complicate interpretation of those very localized measurements. Another problem faced in characterization is contaminant delineation. Again, for the same reasons that borehole data are expensive because drilling is expensive, and we're faced with having to interpolate or fill in the gaps in between locations, and we're looking at very small sampling volumes around the wells. And this again is confounded by problems such as subsurface heterogeneity, and the fact that contaminant transport is not always easily inferred from hydraulic gradients, from measuring heads at sparse locations. Furthermore, contaminants can diffuse into immobile pore spaces that can't be easily sampled from groundwater sampling techniques. So we need new techniques to be able to help with this as well. In tracking aquifer changes over time, again, we're traditionally relying on expensive borehole data that requires drilling, and we're filling in gaps in space, but also filling gaps in time. This figure in the lower left shows how we had a series of different sampling events shown with triangles, and to connect those dots with just straight lines, as you might do in the absence of other information, would fail to capture a lot of the dynamics of this system. This is observed fluid conductivity versus time. At this site, it's a surrogate for total organic acids and the presence of an amendment for biostimulation. With the geophysics shown in the red dots, we're able to fill in those gaps in time with continuous data in time and also really continuous data in space. So to address all of these problems, both characterization and monitoring, we put forward the idea of the geophysical toolbox. And this idea goes back some time. People in the branch of geophysics have been talking about the geophysical toolbox for more than 20 years now, but it's really come into its own in the last few years. The toolbox is conceived as comprising diverse methods for application in different settings and for different goals. No single tool is going to work at every site or for every problem. And so we think of the toolbox as including many different methods that, used in concert, are much more powerful than any individual method used alone. I'll present some studies today that focus on just two of the methods in this toolbox. The toolbox includes many methods that are mentioned again in that Part 1 webinar indicated in the hyperlink in the lower right-hand corner of this slide. But the techniques that I'll discuss today focus on electrical imaging, which involves typically direct current measurements with 4 electrodes. Those electrodes can be in boreholes or they can be installed at ground surface. Commonly, we collect thousands of measurements to construct a single electrical image. You can think of this very much like medical imaging, but applied to the Earth. What we produce with electrical imaging is a cross-section or a 3D volume of the electrical conductivity or its reciprocal resistivity in the subsurface. And electrical conductivity and resistivity are related to lithology, to pore fluid, and to total dissolved solid or specific conductance of the pore fluid. The other technique that I'll showcase today is seismic refraction, and this is also a very old technique that's been in the toolbox for a long time. In seismic refraction, seismic waves are sent into the Earth, generated by a hammer strike against a plate, or use of a weight drop, or a size gun, or explosives. Those waves propagate through the subsurface, and we measure them at different locations with geophones and look at things like arrival time to produce images of the seismic velocity or 1/over velocity, reciprocal velocity, called slowness. Seismic velocity, again, is related to lithology and the presence of water in the pore space. There are many different opportunities for applying geophysics to hydrologic problems. And these are driven by the fact that geophysical data, compared to conventional hydrologic data, are inexpensive, spatially continuous, minimally invasive, and multi-scale. They're inexpensive because they require fewer or no boreholes, fewer if they're collected in between boreholes, no boreholes in the case where the geophysical data are collected at land surface. They're spatially continuous in many cases. We can produce volumes of geophysical properties in the subsurface rather than just looking at sparse locations scattered throughout the aquifer as in borehole data. They're minimally invasive because, again, they require little or no drilling, and they're multi-scale. Many of these measurements can be collected at different scales to inform different scales of heterogeneity. We can collect resistivity at one scale, say the meter scale, ground penetrating radar, sometimes at centimeter or tens of centimeter resolution, seismic at meters to tens of meters. So we can take a multi-scale approach to characterization. The first case study I'll present is from the literature. This is not a study that we were directly involved in, but much of our work on our projects for ESTCP have focused on electrical and electromagnetic methods, and I wanted to give you an idea of other methods that are available. So this is a study involving 3D seismic refraction conducted at Hill Air Force Base in Utah. In this study, seismic refraction was used to characterize depth to an aquiclude and the presence of a paleochannel. This is a test study, so a demonstration study. In the left, you see a map of the site. In the right, you see a slice through the aquifer indicating depth to that aquiclude layer. The depth to the aquiclude layer interpolated here is from the well data. All the dots and circles indicate where seismic data was collected. These data can be collected quite rapidly now with modern technology. In some studies, they're collected with land streamers pulled behind trucks or ATVs. So we have a paleochannel going north-south through the site, and that is evident in the depth to the aquiclude layer. It's incised down into that layer. In the upper left, you have the raw data. This is data collected from a single shot. So this is a waveform at different locations with increasing distance from where an explosive or a hammer strike would occur. And the y-axis here is time. In the lower left, we see the ray paths the seismic energy takes through the subsurface. Those data are put into an inverse model, and the model calibration produces a match to the data seen in the upper right plot, and the result of that inverse modeling is a series of cross-sections, really a volume of seismic velocity through the site. Two of those cross-sections are shown in the lower right. So these are two different cross-sections through the site indicating seismic velocity, which again is related to lithology. The white line in these plots is the depth to the paleochannel indicated by wells, and you can see that the seismic velocity is strongly indicative of this. In addition, the black arrow in those two images is indicating where the water table is, which also has a seismic signature. These are horizontal slices through the resulting models of seismic velocity produced at this site. These three different models are produced from different starting models, and this is a practice common in geophysics to look at the range of possible models that could result from our data, because geophysical models are always uncertain. There's always error in our measurements, and our measurements may not completely inform what's going on in the subsurface. So this is just one of our many tools for assessing the uncertainty of our results. In the middle is the preferred model, preferred in the sense that this is the model that is based on the most accurate starting model based on the information available. But we can modify those starting models, say from the well data, to look at a range of different possible models. The second study I'll present today is from the Hanford site. This is a site in eastern Washington, a Department of Energy site left over from the Manhattan Project in the 1940s and later work at development of atomic and nuclear weapons. The legacy of contamination at the Hanford site, which is about the size of Rhode Island, includes heavy metals, nitrate, and also radionuclides. The environmental concern and the focus of our study is looking at contaminated groundwater, including radionuclides, that's discharging to the Columbia River. We are looking to resolve the hydrogeologic framework at the site. The problem with conventional characterization at the site is that drilling is extremely expensive, and there's a real lack of information about the connection between the aquifer and the river, which is strongly controlled by the geology, in particular by paleochannels and the depth to a contact between two different geologic formations. So this is our general study area. This is the Hanford 300 area. You see the Columbia River to the east. And we are interested both in characterizing the aquifer subsurface on land and also in the riverbed. Here today I'll just focus on the work that we do on land. This is a cross-section through the site showing the contaminated aquifer, the Hanford Formation, which is more permeable, and the Ringgold Formation underlying it, which is finer grained and less permeable. Where that contact is present really controls where the contamination and the groundwater are focused into the Columbia River. So this is the contact that we're trying to map out, and we're looking at mapping paleochannels incised into that Ringgold Formation. Here you see in the left plot a series of resistivity lines north-south through the site, as well as some east-west ones, along which we collected electrical measurements. The type of electrical measurements collected are shown in the middle plot, where you can see some of the electrodes planted at land surface. So this is a technique that involves no boreholes, no drilling. And on the right, a series of cross-sections resulting from the data collection. These are electrical images of the logarithm of electrical conductivity indicating different lithologies. And you can see the Hanford Formation shows up as low conductivity. This is a coarse-grained formation, and the Ringgold Formation below showing up in the reds. That's a much more electrically conductive, fine-grained formation. So those are just cross-sections, but we can, from the data, assemble a 3D volume of the subsurface, a single horizontal slice of which is shown here. So here you have plotted the electrical conductivity at one horizontal slice, indicated by the different colors, and evident in that is a paleochannel controlling the movement of groundwater through the site and into the river. And this is corroborated by other data, including distributed temperature sensing on the riverbed. Temperature is a strong indicator of the interaction between groundwater and surface water, groundwater being colder than surface water in the summer and warmer in the winter. So this is just an example where multiple geophysical methods were used in combination to help provide confirmation. These data also tie in well with a handful of seepage locations identified in previous work by the Department of Energy. At this site, wells cost typically between $50,000 and $100,000. The riverbed itself is extremely difficult to work in because it is armored and cobbly. So this kind of data, although indirect, is providing extremely valuable information to guide characterization and sampling efforts. A question that commonly arises in our work at contaminated sites is, can you directly see the contaminants? And I want to make clear today, to take the opportunity to tell you that we cannot directly measure with geophysics the concentrations of specific contaminants. It's not possible at the field scale. We occasionally can see evidence of contamination, but we're not going to be able to measure concentrations geophysically, whether they're specific contaminants or chlorinated solvents. We can potentially see proxies of contaminant extent. For example, total dissolved solids is something that we can hope to see with resistivity and with EM methods. Redox gradients also are evident in several types of geophysical data, including certain types of electrical measurements. Biogeochemical transformations associated with mature contaminants have signatures at the solid fluid interface. So if there are minerals precipitating, then that is something that we can see the signature of. When we talk about proxies of contamination, again, we're talking about things like total dissolved solids. If a contaminant plume is one with highly elevated TDS, then that does make a good target. That's not to say that we can directly measure parts per billion TCE, but if there's a high TDS associated with a plume that has TCE, for example, then we might. So here is another example from the Hanford site, a very complicated site with a long legacy of contamination of many different kinds. Here we're looking at a tank farm and crib waste disposal site. So these are different facilities for waste storage, and some of these are leaking. And the leaks from these produce high TDS plumes, and that's very visible in the electrical slice through this site. So on the right, you see a map, northing versus easting, with various trenches and various tanks indicated here. And many of these tanks show up as highly conductive features. So this is just an example where we can use geophysics to indirectly map out where contamination is or where it's moving away from some of these tanks. Okay, so that's geophysical characterization. Now I'd like to turn to geophysical monitoring. In geophysical monitoring, we're looking at changes from some background condition. And this is actually a much easier problem. This is a much more attractive problem to geophysicists because it removes a lot of the background geology and the heterogeneity, which aren't our targets. If you're looking for a change from background and you can collect a data set prior to that change occurring, you can resolve much more than you would with just a snapshot collected after the change had occurred. Geophysical monitoring has great potential for use at remediation sites because it can be automated, it can be autonomous. Again, it is easier than the detection problem, and it can complement sampling. We always stress in our work that geophysics is not a substitute for conventional measurements, but rather a complement. And we see it as serving its greatest purpose in filling in the gaps, both in space and time between direct measurements. That figure was from our concept for applying time-lapse electrical geophysical monitoring to amendment-based biostimulation at a site in Brandywine, Maryland, and this was an ESTCP project initiated in 2007, but we are revisiting that site now in ongoing work for a post-audit. The primary objective of the original project was to demonstrate the capability to autonomously image 3D bioamendment distribution with time. On the left is our test configuration showing the distribution of electrodes and sampling wells at the site. We had 7 electrode wells installed into the subsurface as well as trenched-in electrodes at land surface. We had multi-level sampling to provide calibration and validation of the geophysical data. On the right is a baseline ERT image. So this is the background image collected before the biostimulation occurred. And you can see evident in this baseline ERT image the lower confining unit, that's the Calvert Formation, showing up as red, electrically conductive. The aquifer, the Brandywine Formation in the middle, this is lower conductivity, being coarser grained. And then there's some fill near land surface, and this is somewhat finer grained material again. So that's the background image before initiation of the amendment injections. We collected continuous data with only several gaps for a period of about 2 years and generated 3D images of the subsurface around 2 injection points to study how the amendment distributed away from those injection points. We saw a very strong correlation between total organic acids, an indicator of the presence of the amendment, and electrical conductivity from the geophysics, indicating that the geophysics provides strong proxy data for tracking the amendment distribution. Later in the project, we saw a secondary increase in conductivity indicative of mineral precipitation or biological activity, and that is the focus of our ongoing work at the site. So just moving through a few of these images, this is immediately after the first injection at the site at day 5, and you can see over the next year we have elevated conductivities associated with the distribution of that amendment. That conductivity signature decreased in the second year, but then ramped up again toward the end of the project, as you see here, around day 762, indicating again something happening at the fluid-grain interface, either development of biofilms or mineral precipitants. Our second monitoring case study comes from the Naval Air Warfare Center, another ESTCP project. And this involves, again, 3-dimensional electrical resistivity tomography imaging. This site is a fractured sedimentary rock site where the fractures are strongly controlled by the stratigraphy and the distribution of different fissile layers at the site. You can see here the sampling data indicating where TCE is present at the site in these different layers. And we're just going to focus in on a very small area around where 2 different experiments were conducted. This is our experimental layout. We had 7 wells installed with electrodes, a central well ringed by 6 others. And into these boreholes we installed electrodes and packers for multi-level sampling. These electrode arrays were especially designed for our project. These are relatively low cost, and they allow for very high resolution imaging in between wells and fractured rock, and also the isolation of intervals of boreholes for sampling and for injection to conduct tracer tests or introduction of amendments. You can see here in the photo the array going down into the well. This is work conducted by Rutgers University, one of our project partners on this grant. Here's a background image showing the distribution of electrical resistivity in between 3 of the wells. The various conductive features here are indicative of different lithologies, for example, mudstone, as well as fractures. Now, a background image is, again, difficult to interpret in a site that's highly heterogeneous. And so what's very valuable about monitoring is that we get to subtract away a lot of that heterogeneity. These are time-lapse images after injection of a saline tracer. The tracer was introduced into well 87BR, and it was extracted from well 85BR. And we can see where it goes in time in between those 2 wells. And those are indicated, those time-lapse images in the upper right. So these are just a series of snapshots of an isosurface that's like a 3D contour of where that tracer plume is located in between the wells. And we can track this out to highlight, to really illuminate different fracture planes that are conducting fluid and conducting tracer. So that's a tracer study between 2 wells. We also conducted the injection of an amendment at the site to look at where the amendment would distribute. And this involves a different type of injection scenario where there's not an extraction well, there is only an injection well. And you can see in the time-lapse snapshots that, in fact, the amendment distributes differently than the tracer did because of the different hydrologic forcing, the different injection setup, providing further insight into heterogeneity at the site and how the amendments would distribute and how you might or might not hit target zones at the site. So in conclusion, the takeaway messages I'd like you to leave with are the geophysical site characterization can help define the hydrogeologic framework and structures controlling groundwater flow and transport. Geophysics can detect proxies of contaminants and transformation products. However, it is very unlikely that you will be able to directly quantitatively map contaminant concentrations with geophysics. Geophysics cannot visualize contaminant concentration directly. It can, however, monitor for changes. This is a much easier problem than the detection problem. In terms of relevance, 2 ESTCP goals and RPM goals at your sites, we can image the framework, we can look at proxies of contamination, and we can monitor change. And I'd like to use this opportunity to plug a tool that we published at the journal Groundwater just recently. This is a decision tool for identifying methods that will work at sites with specific characteristics. So you enter characteristics of your site and your goals for work at the site, and this spreadsheet tool called the Fractured Rock Geophysical Toolbox Method Selection Tool can help guide you towards selecting the right suite of methods for your problem. In terms of recommendations, geophysical investigations are very valuable prior to drilling, to guide sampling, and to guide the development of your model for a site. You should look to use tech transfer tools such as that method selection tool I just mentioned to help decide on which tools to use in that kind of effort. And in all of our work and all of our tech transfer efforts at the branch of geophysics, we seek to help keep people from being oversold on geophysics, because although there's great potential, there's also potential for misuse and misunderstanding and overinterpretation. And with that, I'd like to close my talk today, other than to just say that the benefits of geophysics are very real in terms of reducing time and cost, expanding spatiotemporal information and filling in the gaps in between wells, and allowing you to look at characterization and monitoring at different scales so that you can develop scale-appropriate information for parameterizing flow and transport models and making predictions about contaminant transport or about the effectiveness of different remediation strategies. Thank you very much. Other people involved in our project are listed here, including partners at Rutgers University and Pacific Northwest National Lab. Thank you.
Thank you, Fred. I'd like to remind our audience to submit questions at this time by using the chat box on the left-hand portion of your screen. We have received a number of questions on this first presentation that Fred will answer. First, Fred, a question from the Army Corps. Can you please elaborate on the methods that can detect redox gradients and what the methods are directly measuring?
Sure. Spontaneous potential is an electrical measurement that's very easy to collect, and it involves no application of current, in contrast to the direct current measurements that were the focus of three of today's case studies. Spontaneous potential has been used in mineral exploration and petroleum for 80 years or so now. It's only in the last few years begun to see real application in environmental studies. One of the complicating factors with it is that it is affected by other signals, including the movement of water itself. But SP has great potential for mapping out redox gradients. That's the technique that I was referring to there.
Great, thank you. Can you please describe the field requirements for performing vertical seismic profiling in terms of the number of borings or surface monitoring locations required to calibrate the model to sufficiently understand the depth of key features? And this question was prompted specifically by the Hanford case study.
Okay. Vertical seismic profiling is not a technique that we've done a lot of at the branch. So I can't say that I'm an expert in that. We didn't use VSP at Hanford ourselves. With vertical seismic profiling or vertical reverse seismic profiling, you're shooting seismic energy in between land surface and a borehole. And so what you can come up with from that is a tomogram, a cross-section of seismic properties around the well. Sometimes those data will be collected in different transects leading away from the well at different angles, so that you could almost get a quasi 3D image. But the resolution varies a lot as you move from where there's a lot of coverage, which is near the borehole and near land surface, to farther away. So in terms of the design of those experiments, it's tricky, and the resolution does vary quite a bit. I'm not sure that I can fully answer the question without digging into this more and drawing diagrams to help with this. But I would encourage the person who posed the question to get in contact with me offline.
Okay, great. Next, a question from the oil industry. Can you speak to the ability or the limitations of using surface resistivity measurements alone to delineate shallow soils impacted by hydrocarbons?
Sure. So if you have pure phase, non-aqueous phase liquids in a porous medium, they will have a resistivity signature. So in principle, it's possible to see that. The problem is that as petroleum degrades, it can go from being resistive to being conductive. So this can be pretty complicated looking at a plume of, say, petroleum with resistivity alone. Often when we collect resistivity measurements, we also collect induced polarization measurements or other measurements. Resistivity and IP, they're almost the same measurement. They're collected with the same equipment. And one, resistivity is very strongly affected by the pore fluid. The other, IP, is really not affected by the pore fluid so much as the lithology itself. Having those two measurements together can help us constrain interpretation for things like hydrocarbons. But again, I'm always cautious about telling people about the capabilities for directly sensing contaminants with geophysical methods. So just be cautious about that. And again, if this person would like to get in touch with me with further follow-up questions, I'd be happy to help.
Okay. The next one is a question from EPA. Can you offer an example of where geophysics has been used at a small site? So for example, characterizing a release at a gas station.
Geophysics has been used at many sites, including gas station-sized sites and landfill sites. And there's an excellent case study that came out of the branch of geophysics largely before I came here at the Yukon landfill, the University of Connecticut landfill. I wouldn't call it a small study, but it's a relatively small site. And Carol Johnson, who's speaking next, produced a series of reports about that. I would direct the person asking this question to our branch publications page, where we have listed many USGS reports and articles from small sites just around military bases, and there are landfill studies there, and that might be a good place to start.
Okay. Next, would vertical seismic profiling work with a case borehole?
I believe that could be possible. I have no experience with that myself. So I do not know the answer to that question. Vertical seismic profiling is not really in our, that's not in my personal toolbox. It's certainly in the geophysical toolbox. But I'd have to refer you to somebody else here at the branch to answer that question. So if you could get in touch with me offline or look for John Lane's contact information. John does a lot of the seismic work here at the branch.
Okay, great, thank you. And one last question for you, Fred, before we move on to the next presentation. You've discussed and showed images made from data collected at the land surface and also from boreholes. What are the advantages of each approach?
Great question. We commonly prefer data collected from boreholes because they provide more information to resolve in between the boreholes, resolve things that are deeper. So we tend to get higher resolution images if we have access to the borehole data. The real advantage of the surface data, though, is that you don't need to install a well, so you don't need to drill, and these become much less costly. The data analysis also is streamlined by software that's publicly and commercially available. So, for example, with surface resistivity data, this is very cheap data to collect, very easy to work up. The borehole resistivity data is a little more difficult to collect, and it does require wells.
Okay, thank you, Fred. And Fred will return for our second question and answer session at the end of the webinar.
Okay, thank you.
Thank you. The next part of the webinar will be presented by Ms. Carol Johnson, who's a hydrologist with the USGS Office of Groundwater, Branch of Geophysics in Storrs, Connecticut. She provides leadership to USGS hydrologists nationally on the development and application of hydrogeophysical methods to USGS groundwater studies through applied research, training, and policy development. Her research interests include the use of borehole and surface geophysical methods and hydraulic testing for the characterization of fractured rock aquifers. She has co-authored approximately 40 USGS publications on the use of hydrogeophysical methods for aquifer characterization for water resources and contaminant investigation. She currently holds a professional geologist license in New Hampshire and serves on the board of the Environmental and Engineering Geophysics Society. She has a bachelor's degree in geology from Bates College and a master's degree in hydrology from the University of New Hampshire. Carol?
Thank you, Jennifer. The overview of this presentation includes a brief discussion of what is borehole geophysical logging, and we'll follow that with a discussion of tool selection, objectives for borehole geophysical logging. We'll discuss logging results and how they're used for other survey designs, and we'll close with the benefits to DoD sites and a summary. So borehole geophysical logging is, in general, a system of equipment that can be lowered, can lower tools into a borehole and collect point or continuous data and transmit that data to the surface for digital storage, processing, and analysis. These data provide depth-dependent measurements of hydrogeologic properties that are potentially critical for site characterization, for planning well completions, for designing sampling, monitoring, and remediation strategies, and for performance monitoring at DoD sites. The tool selection should be based on the properties of interest and the objectives of the investigation. The Fractured Rock Geophysical Toolbox was introduced in the first presentation in this series by Lee Slater and was also discussed a little earlier by Fred Day Lewis. The FRGT is an Excel-based utility to support the cost-effective selection of borehole geophysical tools that are appropriate for the site condition and project goals. In this presentation, we'll not cover the use or application of the specific tools, but we'll encourage you to explore the FRGT method selection tool, where it will go over in more detail the information on each method. And as Fred indicated, you can get information on the likelihood of success and some of the potential limitations for each method at your site. In this presentation, we'll cover the overall goals for the purposes of doing borehole geophysical logging at DoD fractured rock contamination sites. There are several objectives for borehole geophysical logging, including the characterization of well construction and integrity of the borehole, for characterizing the geology, structure, fluids in the formation and fluids in the borehole, and for characterizing the hydraulics and hydrogeology. In addition, borehole geophysics can be used to design well completions, for planning other surveys, or for corroborating the interpretation of surveys, such as using the methods described by Fred. Borehole geophysical methods can also be used for monitoring transient processes. So Borehole geophysical logs are used to characterize the borehole conditions. This is particularly helpful in existing boreholes of unknown construction. And because boreholes are so expensive to install, we want to use all the available wells. So it's critical to use several of these tools that can be used to characterize the condition of the borehole. And this includes characterizing the depth, the diameter, the casing materials, the cement bond, and integrity of the hole, such as the presence of obstructions, foreign objects, or collapse features. This information can be helpful for avoiding problems and for additional tool selection. For example, the presence of steel casing might limit your tool selection. Also, caliper logs that provide borehole diameter information can be used to optimize packer locations or to determine the pump and other equipment placements. And it's very important that these tools are calibrated. In the example on the left, the caliper indicates two enlargements, one near the bottom of casing and the other at a fracture at depth. Both zones require some caution when installing equipment and for removing equipment near these zones. So it really does underscore the need that our tools are calibrated and that those dimensions can help us figure out how these packers will fit. Another critical condition of the borehole is the deviation, or its XY location with depth. And deviation data are necessary for correcting all structural logs, and they're absolutely critical for any hole-to-hole surveys. Borehole logging can also be used for characterizing the geologic framework by identifying the stratigraphy or the lithology. These methods can include nuclear, such as gamma, electrical, seismic, or imaging logs. In the example to the left, the gamma, optical, and acoustic images were used together to determine the stratigraphy. Collectively, these logs can be used to identify sequence stratigraphy and structural features, such as the location of bedding plane fractures and or potential water-bearing zones. And we can put these logs from the individual wells together, and in this slide we can see the data from multiple wells, and we can see how these logs are used to correlate specific beds across the well field and across the site. Here at the NOC site that Fred introduced, we show a marker bed noted by the gamma peaks. And we can also see that there are continuous bedding plane fractures and water-bearing zones that can be traced across the well field. This example highlights that borehole logs are clearly helpful to characterize the geologic framework, which is important for developing a conceptual site model. The geologic structure can be characterized by identifying the orientation or the strike and dip of fractures and lithologic contacts. These methods typically include optical, acoustic, and resistivity imaging tools. The example on the upper left shows the ATV and OTV images and a trace of the two fractures in this gneissic rock. Below the images, we see the interpretation of these fractures shown in tadpole and stereo plots. Collectively, these tools can be used to map fractures and characterize the network and potential pathways for fluid migration and contaminant distribution. Structure is important for the site conceptual model at fractured rock sites. So to get the correct structural orientation, it's absolutely essential to consider the borehole deviation. Few wells are truly plumb, so we have to include borehole deviation. And we also have to consider the magnetic declination and borehole bias when we're dealing with these data sets. And this is important to apply these corrections and to document the deviation and declination corrections, especially as we start upscaling from the borehole to well field scales and to site scales. The characterization of fluids includes the fluids in the formation, which are typically determined with both electrical or electromagnetic measurements that characterize the area around the borehole. And we can also characterize the fluids within the borehole in the fluid column. And from that data, we can infer zones of different water chemistry and infer zones of vertical flow. And inflow zones can be identified by comparing fluid profiles that are collected before and after imposing some stress like pumping or injecting fluids. In this example on the left, the ambient fluid profile in blue suggests water is moving vertically in a borehole from one fracture to another. Under pumping conditions, shown with the red dashed profile, we can see a different water chemistry in the water column coming from the fracture near the bottom of the well, and we can see vertical displacement in the fluid profile. So monitoring change in response to a stress is very effective for identifying inflow zones. Another means to characterize the amount of water in the formation around boreholes uses nuclear magnetic resonance. NMR is a well-established technology in the petroleum industry, and recently it's been designed to be developed for environmental applications, with tools fitting into boreholes with casing sizes as small as 2 inches in diameter. NMR directly measures the water content in the formation, and that can be used to estimate pore size distribution and permeability. In this example, the NMR shows what's called the T2 decay, and that's used to determine the pore size distribution, the total water content, and the proportion of bound and mobile water contents. Here, the water content in black correlates very well with the neutron log shown in red. And NMR does not require any active nuclear sources that require licensing, permitting, and extra precautions. There are several geophysical tools that can be used to measure flow and monitor changes in response to hydraulic stress. And these include the flow differencing logs, as we described already, and also flow meter logs, which are collected under ambient and stress conditions using a heat pulse flow meter, an EM flow meter, or a spare flow meter to measure the vertical flow in the boreholes. Some other methods include high-resolution temperature logging to detect flow, as well as dye tracers, tracer pulse, and dilution methods to monitor time sequence and vertical displacement of the tracer in the borehole in order to measure fluid velocity and flow. In the example shown to the left, these tracer logs usually include establishing some sort of a uniform background in the water column, such as the blue T1 curve. And then in this example, allowing the natural upflow conditions to displace the tracer over time. And from this, we can determine the velocity and the flow rates and characterize the inflow zones in the well. The collection and analysis of these methods are described by Miroslav Korb and others. So the vertical flow profiles obtained in boreholes can be modeled quantitatively or qualitatively. In the qualitative model, it's simply determining where is the inflow and outflow location. Or the profiles can be modeled quantitatively to estimate the transmissivity in the head of discrete fractures or fracture zones. One example of a quantitative model is flow log analysis of single holes, or FLASH, which is an Excel-based utility to solve multiple simultaneous flow equations by adjusting the discrete zone transmissivity and heads to model the ambient and stressed flow profiles such that they match the observed flow profiles. And this is an extra step that we can take with our existing flow meter logs to get some very important transmissivity and head information critical to the conceptual site model. In addition to using borehole logging for characterization purposes, borehole geophysical methods are crucial for planning the completion and construction of wells, which might include the placement of temporary or permanent packers at specific locations, the use of borehole liners, or for guiding the construction of conventional multi-layer wells. Once the borehole logs are collected, they can be analyzed rather quickly and used to plan other tests, such as single-hole packer testing, or to determine the placement of packers for well field scale hydraulic testing, or selecting the location and spacing of resistivity arrays for electrical imaging methods. And borehole geophysical logs, specifically the fluid and the flow profiling tools, are indispensable for locating injection or sampling zones, or for designing long-term monitoring systems. In this example from the NOC site, it shows the well field with the ATV logs for each well and the location of the packers superimposed on the wells. And then the packers were set for cross-hole aquifer tests where single zones were pumped and all other zones were monitored for head and drawdown as part of a field test using hydraulic tomography. So the potential benefits of the logging program are to identify the sources of water to wells and to identify the transmissivity and heads of fractures and fracture zones. And with this, we can design sampling and monitoring systems with the consideration of flow regimes. So we can isolate or make use of the flow regime for sampling, and we can prevent cross-contamination. It's important looking at these flow regimes so that we can collect meaningful samples. And we can reduce the cost by targeting sample zones, by targeting our sample zones and avoiding samples that might represent a mixture of zones. To illustrate this point, we can consider an open hole with two fractures, one at the top and one lower in the well. If point sampling were collected along the depth of the borehole, we'd obtain a chemical profile that looks like the one shown here. And we'd have a sense that there's some vertical flow in the well, but we wouldn't know the direction or the magnitude of the flow, and we might think that the contamination is widespread with depth. If we used a flow meter tool, we would identify that there's some downflow here, shown at a rate of -1 gallon per minute. And we'd know from the flow meter along with the head profile that the upper zone has a higher head, the lower zone has a lower head with this vertical downflow. And we'd identify that the contamination is in the upper zone and that it's being cross-contaminated to the lower zone. However, if we measured with the flow profile first, we could use that information to plan the sampling, and we could isolate these two zones, either with pumping or with packers, and we could characterize the water chemistry with two samples rather than with multiple samples, thereby reducing the sampling and avoiding collecting samples that might not give a clear picture of the subsurface. So in summary, borehole geophysical logging is used to characterize the hydrogeology of the site and improve the understanding of the structure, flow conditions, transmissivity, and head, all of which can inform the site conceptual model. Borehole logs are effective for planning other geophysical surveys, such as the electrical resistivity or hydraulic tests. Borehole logs are critical for designing the well completions and for preventing cross-contamination. And geophysical logs should be interpreted together to corroborate the interpretation with multiple lines of evidence. And they can also be used to constrain inverse models along the borehole in hole-to-hole surveys, such as the ones that Fred showed today. In conclusion, the tool selection should be based on the project goals, the objectives, and the site conditions. And there's no one single tool that can do it all. There's no silver bullet. Multiple tools should be used together to enhance their interpretation and to avoid or minimize non-unique solutions or interpretations. An appropriately applied borehole geophysical logging program can improve the conceptual site model It can be used to design meaningful sampling strategies, as well as effective remediation and monitoring programs at DoD sites. And finally, I'd like to acknowledge the other people who have worked on this project, including Fred Day Lewis from my office and Lee Slater and Judith Robinson from Rutgers University.
Okay, thank you very much, Carol. We have a few questions for you at this time. The first is, what does the new NMR technology provide that neutron logging does not?
So nuclear magnetic resonance can distinguish the pore size distribution, and it can provide information on the water fraction. So you can actually see the amount associated with clay, capillary, and mobile fractions, whereas the neutron can't. It just will give you a total fluid content or water content.
Okay, thank you. And can NMR distinguish between hydrocarbons and water?
Yeah, that's a really good question. This has been done in the oil industry, and efforts are being made to make the same sort of measurement using the environmental equipment and for environmental applications. And there's really ongoing work to try to bring that technology and make it possible and easier for doing in the environmental well fields. But right now it's still in the development phase. So some work to look at would be some work being done by Emily Fay of Stanford and some work by Elliot Grunwald of Vista Clara.
And can NMR be used in cased boreholes?
Yes, that it can be used in PVC cased boreholes, but it can't be used in steel cased holes. And it can also be used in open hole wells.
Okay. You talked about flow meter tools. The term dynamic resolution is often used in association with the discussion of flow meter tools. What is that, and how does it differ from the tool's resolution?
Yeah, so each tool has a tool resolution, some minimal amount of flow that it can measure. But there's also a dynamic resolution that we have to consider. And so a flow meter will only see features that are within 1 to 1.5 orders of magnitude of the most transmissive fracture in the well. So in the presence of a big booming transmissive fracture, we're not likely to be able to see a very minor fracture at the lower end of the tool resolution. If that big booming fracture wasn't there, then we would be able to characterize that with within the resolution of the tool itself. So we have to keep that in mind. So if you see very transmissive fractures and no others, it might be that there are still some minor transmissive fractures in the hole. We're just not seeing it with the flow meter because of the dynamic resolution.
Okay. And why is it important to do flow meter logging under both ambient and stressed conditions?
So so some people want to do just one or the other. But if you consider under ambient conditions, you have two very transmissive fractures in a well, but they both have the same head, they won't have flow from one to the other. So the flow meter won't help you identify those fractures. And if you just skipped to doing pumping or stressed flow meter logs, and you did have some sort of ambient flow in the hole, then you won't be properly proportioning your transmissivity to those boreholes. So it's really important to identify if there's ambient flow so that you can factor that into the flow profiles under pumping conditions. And then you'll get proper transmissivity estimation.
And for imaging tools, would you use ATV or OTV or both?
Yeah, so ATV requires water in the borehole, and the OTV requires clear fluid or an open hole. And so it's very site dependent. So in some places you can only use one or the other. But in general, if possible, I'd use both, as you could get the best interpretation using them together.
Okay. And one last question for you, Carol, before we bring Fred back for some questions as well. What do you see as a priority for geophysical logging programs? What's most important?
Yeah, I think it's always important to test and try new tools at sites where we know what the characterization is, so that we can really test this new equipment. And I also think it's really critical for us to save the actual data and be sure that they're preserved in some digital form and that they're well documented for the site and for future use. And I think that having that database will provide a historical reference for both new logs and for the site, or site history.
Okay. Thank you very much, Carol, for the presentation and for answering these questions. At this time, we'd like to also have Fred back on the line. There were a number of questions left from Fred's presentation, and we'll ask a couple of those then, and then there are some general questions for both of our speakers today. So Fred, the first question specifically for you is a request to please discuss how near-surface features, things like utilities, pipelines, and electrical conduit lines, could interfere with trying to use electrical resistance imaging to track the subsurface distribution of amendments or other monitoring that is being attempted.
Sure. Those kind of things, utilities, pipes, are extremely problematic for electromagnetic and magnetic methods. For direct current resistivity, they are less so, especially if you know where they are. They can be included in the model so that they don't really interfere with interpretation as much. But they do add complexity. It is an issue. But we don't get as much like electromagnetic interference for problems with DC resistivity as we do with the EM methods that are very susceptible to that. So that in most sites we can still do resistivity.
Okay. And Fred, which amendments have geophysical signatures?
Well, we've worked with molasses, with ABC, which is short for anaerobic biochem, with vegetable oil emulsion. Those I know have strong electrical and or dielectric signatures. I believe people have also worked with geophysical monitoring of EOs. If an amendment has an additional pH adjustment associated with it, those pH adjustments typically have very strong geophysical signatures, so it's as if you were doping the amendment with something that you can see even better. But these are things that we can determine in the lab. And of course, they all depend on the concentration or the mixture of the amendment with, for example, water that would go down with it too.
Okay. And Fred, what sort of resolution can you achieve using the electrical imaging method?
This is one of those questions that's important and often difficult to answer. We can, with resistivity measurements, get resolution on the order of centimeters if you're spacing the electrodes very, very close together, as we do in the lab. In the field, it depends on many factors, including the spacing in between the electrodes that controls the best possible resolution you could achieve. Also, the actual electrical conductivity structure of the Earth that focuses the current where it goes and where it doesn't go, and the noise levels that are present. And that is something that is site dependent. So some places we have noise in our measurements on the order of 1 or 2%, other places it might be 5% or even worse. So all those things factor in. I would say that in much of our work, we're looking at resolution on the order of a meter or somewhere around that, maybe a few meters, and that's for both the cross hole and the surface arrays. Now that said, resolution varies where you are in the image too. So it tends to get worse with depth if you're looking at surface resistivity, and it's worse far from the wells in the case of cross hole resistivity.
And is there a geophysical method that can measure hydraulic conductivity directly, Fred?
Carol talked about nuclear magnetic resonance and flow meter logging, and those techniques are probably the most direct ways we have of measuring hydraulic conductivity with geophysics, especially the flow meter logging, which you could think of almost as a hydraulic test. It's really another type of aquifer test. But nuclear magnetic resonance is the one that we're really looking at to measure hydraulic conductivity, just as it's used to measure permeability in the oil field.
Thank you. Carol, do you have anything to add to that? Do you concur with it?
Yes, I think Fred's right that the flow meter is like one of the most direct measurements for hydraulic conductivity, and NMR is really effective for estimating hydraulic conductivity. And again, the well doesn't even have to be open to the formation to be able to sample it. So you could have a PVC cased hole, and you can still effectively get information like a slug test from behind the casing. So that's I think that this tool can be used in many sites with existing wells, even if they're not open to that part of the formation.
Thank you. The next question is primarily for Carol, but Fred, if you have anything to add after Carol addresses it, please do feel free to do so. Carol, if borehole geophysics has already been collected at a site, are there instances where there would be logs that you would recommend adding or repeating?
Yes. So as Fred indicated, conditions change over time, and there are several tools that can monitor those changes, like the fluid electrical conductivity log. The EM or electrical methods are really effective for monitoring those spatial and temporal seasonal changes. And of course, Fred showed the effective use of long-term monitoring with the ERT arrays that can sample over time. Another log that isn't really considered that often for looking at change over time, but one that we saw at the Knox site is that the boreholes themselves will change over time, and especially in these sedimentary rocks where zones will, the rocks will cave in, the fissile zones will decay, and the boreholes will enlarge. And so I think if you're going to be putting a very expensive tool or a packer into a well, I think it's well worth it to rerun your caliper tool and find out what those borehole conditions are as they do change over time.
Thank you, Carol. Fred, anything to add to that?
No, I really don't have much to add to that.
One more question from the audience. How do you differentiate between the many push-pull technologies such as HPT and traditional borehole geophysical logging? And let's start with Carol for that.
So the traditional HPT is in direct contact with the formation, right? In sediments, whereas for traditional borehole geophysical logging for sediments, you'd have a cased borehole. So I think I think our NMR tool is going to start to get at very similar information that we can get with HPT, but through the cased boreholes.
Yeah, I'll just add to that I think this is a really exciting area of overlap where direct push technology and geophysics are now being used together and really dovetailing. And some of the work that we're doing right now involves using direct push to install very low-cost electrodes and sampling ports at sites to do resistivity tomography. And you're seeing also electrical logs being collected with direct push technology. I guess the real difference is just whether or not you end up with a well there that you can sample subsequently or not. But even some of the arrays we're putting down, you'd hardly call them a well. It's just tubing and electrodes. So it's a really exciting area, and there's a lot of opportunity for growth and technology development around combining geophysics and direct push.
Great, thank you both. The next question, are there geophysical methods for measuring water level fluctuation in an aquifer during a pumping test where there are no monitoring wells? Fred, let's start with you for that question.
Sure. I can think of a few examples in the literature where ground-penetrating radar, shallow seismic, and also spontaneous potential have been used to monitor pumping tests. With radar and seismic, you can look for water table or saturation, really, so you have to worry about capillary fringe. With SP, you can actually look for flow directions and thereby get at anisotropy in the flow around a pumping well. So those are the three techniques I can think of as having been published for that application.
Carol, do you have anything to add on that one?
No, I also was thinking of the GPR, the radar, which I think was very effective for seeing those water level declines and not having some of the issues with that capillary fringe that you were talking about. So yeah, that's the one I'd point to.
The next question is about Fred's presentation, the Brandywine case study. How did you confirm that the geophysics was actually seeing the amendment? And how do you know that the long-term changes were related to biological activity?
Thanks for that question and for the opportunity to add a little bit more on that. We had, I think it was, it was probably about 23 sampling ports where we collected fluid samples for analysis and also for field parameters to develop a correlation in between the geophysical measurements and what we were seeing for the amendment presence expressed as total organic acids. And we had R-squareds on around 0.9 for that relationship. And that was based on a small subset of data that was collected at one sampling event. Then we predicted what we would see months later. We collected more geophysical data, took it, made a prediction, and then had a sampling event and showed that relationship held up. And despite changes in the system, we were still able to estimate what the total organic acids would be at that time. So that was a calibration validation exercise that we conducted for total organic acid estimation. As for the biological activity, this is the focus of ongoing work. We looked at how resistivity changed over time, and that relationship that we calibrated actually evolved during the course of our initial project. So at the end of that initial project, when we'd been monitoring for about 2 years, we saw bulk conductivity increasing in the geophysics, but fluid conductivity was not. It was still declining. So we could not explain at that point what was going on in the geophysics in terms of the total dissolved solids of the pore fluid. They were not moving in concert anymore and were instead deviating. And the only real good explanation for how that could happen is if there was conductivity developing right at the grain boundary, the fluid-grain interface. And that could happen by two different things, two different factors. One being biofilms, which have been shown to be conductive in some work, or by mineral precipitates that are conductive, as in the case of iron precipitates, which is something that's expected with this kind of bioremediation. So that was how we developed the hypothesis around biological activity or mineral transformations. And that's being confirmed, hopefully, in our ongoing work. And I'd hope to tell you more about that perhaps in a year's time.
Thank you very much for the additional explanation, Fred. There's one last question. It's for both of our speakers. Given that all geophysical methods will not necessarily work at a certain site, how can you predict whether the application of a method will be successful? We'll start with Carol with respect to borehole geophysics.
Yeah. So again, I'm going to point to that FRGT fractured rock geophysical toolbox utility that we have. And what we've done is we've gone through and listed for tools that maybe don't work in a highly conductive zone. And if you say or a highly conductive site, you say you have clay at your site that's really highly conductive, then we've given poor ratings to the likely success, let's say, of using anything like EM or GPR, borehole radar, because that signal will be quickly attenuated. So, so we've gone through and tried to go tool by tool and try to highlight what will be likely successful in certain settings and what will likely not work in certain settings.
Thank you very much, Carol. Fred?
I think, like Carol said, that method selection tool is a good place to start for fractured rock. We intend to publish other similar tools for other environments and goals aside from fractured rock. So keep an eye on the branch webpage for those. In addition, I'd like to say that at the branch, when people call us and ask, will this method do this? Or what would I see if I applied this method at my site? Can you see this kind of target at this depth? We usually get on the computer pretty quickly and run what we call pre-modeling. This is something that Lee Slater spoke about in part 1 of our webinar series. And the workflow for pre-modeling is that you start with a hypothetical model, basically your best guess for what it is you're looking for. You could just sketch the target at that depth embedded in some geologic framework. And we can take that and we can predict what data we would collect for that hypothetical target, add some random error to it, and analyze it just as we would real field data to come up with an image for what we might see for that hypothetical target. And if the image that results from that process doesn't reveal the target, if it's lost amidst the heterogeneity or because of the kind of noise levels that you expect, then there's really no point in doing the survey. So that pre-modeling exercise is invaluable to keep from going out and conducting a survey that's doomed to failure and to keep from having geophysics oversold. So I would encourage people to either conduct that exercise or ask contractors to conduct that kind of exercise as a proof of concept that they can do on the computer for a numerical gut check.
Thank you very much, Fred, and thanks to both of our speakers, Fred and Carol, for the excellent presentations today and the question and answer sessions. The next webinar in this series, thank you. The next webinar in this series is on August 11th. and it is an environmentally acceptable alternative for fast cook-off testing, demonstration, validation, and implementation efforts. The webinar will feature Dr. David Hubble and Dr. Ephraim Washburn as speakers. Registration is open for this webinar soon, so visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.